This talk is very significant for me because I've given many talks at this seminar. And if you go to the web page, there's these tags on the side, and then with this talk, I've passed up Andreas as the biggest name. So I measured the font size. I'm now bigger than. So the more machine learning title of this talk is Structure Learning of H colorings. It's a nice talk because it's everything is very elementary. So I can state the problem, it's very easy to understand, and all the proofs are, I can give you basically the proofs here. Maybe you'll come up with them once I tell you the results. So we're talking about colorings of graphs. So here's a graph on 3 vertices, just a path of length 2, and then here are all the 3 colorings of this graph. Okay? So let's just some general context about colorings. So let's say I'm looking at K colorings and I'm looking at a graph of max degree D. Then what do we know? Then we know if there's if the number of colors is bigger than the max degree, then you can always color it with the greedy coloring. Now what happens when K is at most the max degree? Well, then there's this interesting threshold that comes up. Well, sometimes there certainly are graphs where it's not colorable, and there's some graphs where it is colorable. Okay, so you might ask the computational question, can I figure out, if I give you a graph and I give you a K, can you figure out whether there's a K coloring or not in polynomial time? Okay, so there's a very beautiful result, this amazing result of Malloy and Reed, which shows that there's this threshold at D, roughly D minus square root D, and when the number of colors is bigger than that, then in poly time you can check whether there is a K coloring or not. And when you're below that threshold, then it's NP hard. Okay? So actually, I mean, I'm doing this for background, but also because we're going to get some result which relates actually to this thing. So when K is less than K minus square root D, plus some smaller order term. Okay? So, okay. Now, a natural question that you might ask, and that I've done a lot of work on, is if I give you the graph, can I sample from this space of colorings, uniformly at random from this space of colorings, efficiently? Okay? So the terminology is more that I have omega as a set of all colorings, and then I want to sample from the uniform distribution on this space. That's called the Gibbs distribution. Okay? And I want to do it in time polynomial in the size of the graph. N is the number of vertices in the graph. And the key thing is that this space, omega, is huge. It's usually exponential in n, but I want to sample from it in time polynomial. Okay? So, okay, so I mean, we're gonna do kind of the backwards of this problem, but I just want to give you context on this, actually, because this is going to come into play too. So when can we do this efficiently? Well, I had something from my thesis that showed when the number of colors was greater than 11 over 6 times the max degree, then you could do it efficiently. And that was the best, actually, for general graphs until just like 2 months ago. Somehow, two different groups improved it by some little epsilon. Okay? And then, but what's important, actually, is this conjecture. So the conjecture, this is going to come into play too, is that when K is bigger than D plus 1, then you can do it efficiently. Now, why do we conjecture K bigger than D plus 1 that you can do it efficiently? This corresponds to something that's known as uniqueness of the Gibbs measure. Actually, so I defined Gibbs measures for a finite graph as a uniform distribution over the space of colorings. In physics, statistical physics, they're interested in infinite graphs like ZD, the integer lattice. And you want to know whether there's these Gibbs measures that you define on finite graphs they correspond to measures on infinite graphs by taking limits is one way. And then you want to know whether there's a unique measure on the infinite graph or multiple measures, non-uniqueness. Okay? So this corresponds to uniqueness. What does it mean? Another way to see it is if I take a tree, how this D plus 1 comes into play. K greater than D plus 1. I take a tree, a D regular tree, or I guess branching factor D minus 1. D minus 1 branching tree. Okay, and I got this root here, R, and then I'm doing a tree of height H. Okay, and now you put some boundary condition here, some coloring of the leaves. Let's call it tau H. Okay, put some coloring of the leaves, whatever you want, and then do a random coloring of the tree, conditional on that, and then ask, let's say, I want to know whether the leaves influences the root. Okay, so I'm going to look at the marginal distribution, let's say the probability, let's say pH, and it's a function of tau, and this is the probability that the color of the root is whatever color you want. Let's say color 1. Okay, and then, so I want to know whether for all sequences of, so if it's a finite tree, then certainly it's easy to construct that almost every coloring of the leaves is going to have some influence on the root. And the question is, when you take the limit, so I want to know when I take the limit as the height goes to infinity, I want to know whether pH, whether it's marginal, whether the influence of the leaves dies off. And then, so I want to know whether that, how that compares to, whether that equals 1 over k. Okay? And then the point is that when k is bigger than d plus 1, then for all tau, it dies off. It's equal to 1 over k. And when k is at most d, then there are boundaries which influence it in the limit. Okay? So, anyways, this one is going to come into play. So I wanted to bring that into play. Okay? Please ask if you have any questions, because it's going to be too short of a talk otherwise.
So you know when k is bigger than like 11 over 6 times d, or?
Oh, yeah. This, I mean, this thing is about trees, but it's known. Yeah, so it's known for trees that the phase transitions happens at k equals d plus 1. Now, why does that have anything to do with this thing? Because this is about general graphs of max degree d, and the intuition is that trees are the worst case. So, or tree-like graphs are the worst case. So if you want me to color a tree, I can do it. I mean, anybody can do it in polynomial time. But graphs that are tree-like, like a random graph, are the worst case. So they're what makes it hard, actually. So that's why the conjecture. Oh, and then...
Is the uniqueness considered through mixing time?
Oh, how does it come in? No, it's just uniqueness doesn't come in actually to the mixing time. It's just that's our intuition about why we make this conjecture that is true, is because we think trees are the worst case, and then in the uniqueness region we think that there should be an algorithm. You should be able to do it efficiently because these correlations die off quickly. Actually, not only does it go to 0, it dies off exponentially fast. Or that's the conjecture. Actually, we can't prove that. So, yeah. Okay. I mean, we can for some models, like independent sets.
But then certainly it is related to the mixing time. But it dies off exponentially fast, right?
Yeah. Yes. I mean, there is. Well, this connection is known for things like independent sets. When you do the this hardcore model, then there is connections known. You need something stronger than the way I define uniqueness. You need something called strong spatial mixing, which maybe I do it on the board later after the talk. Okay, so the question I asked on the previous slide was, I give you the graph, can I sample from the uniform distribution over colorings? Now I want to flip it. I want to reverse the question. So now I'm going to give you samples from the uniform distribution, and then I want to ask, can I figure out the graph? So I don't know the graph, but if you give me samples, can you figure out the graph? Okay? And then if you can do it, so first off, the first question is, does the samples, if I give you infinite number of samples, does that uniquely define the graph? So that's statistical identifiability or non-identifiability, okay? And then the second question is, if it does uniquely define the graph, how many samples do you actually, computationally, how hard is the problem? How many samples do you need to figure out the graph? Okay, so what can you do the algorithm is very simple. You can't do anything actually, right? I mean, what can you do? I mean, you want to figure out whether for this pair of vertices u and v, is there an edge there? So how can you tell? Well, certainly you know there's no edge if they get the same color in some. If they both get blue, then you know there's no edge between them, okay? And that's actually the only thing you can do for this problem, okay? So all that matters is the analysis of this algorithm, okay? So does this work? So first off, well, what can happen? Well, first off, maybe, I mean, you might construct an example where u has some color, and then it's got a neighbor w, which is different color, and then maybe v gets different color than w, and then maybe because of parity, they get the same color, okay, or something like that. So is there an example where u and v are not connected, they're not adjacent, but they always they never receive the same color, okay? So you never have a proof that they're not adjacent. Then it's not identifiable because I could add in the edge between u and v or leave it out and it doesn't matter, okay? Because they always get different colors, okay? So then you can never tell the difference between that graph and that graph with the edge between u and v. Now the other problem is maybe this doesn't occur, but maybe what might happen is that the probability that they actually receive the same color is exponentially small, and then we're going to need a lot of samples, okay? So there's two things that can go wrong. Okay, well first off, you can force it so that u and v get different colors. Here's this graph. I got 3 colorings, okay? And what I'm going to do is I'm going to make u and w, if you notice, u and w always get the same color. Therefore, v gets a different color than w. Therefore, u and v are, u and v never receive the same color, okay? Yeah, so you can never tell the difference whether this edge is there or not. Okay, why? Because the middle two vertices, right, get 2 colors. So let's say color 1 and color 2, and then u has the 3rd color, and w also has that same 3rd color. So, okay? So that's a simple example when we got 3 colors, and we have a graph of degree 3. Of course, if you think about it for half a second, and probably a lot of you already did, you notice that you could just generalize this, right? If I have k colors, then I replace this thing by a clique of size k minus 1 in the middle. And then I'm going to get, but this only works when the number of colors is the max degree, okay? Or if the number of colors is smaller than the max degree. But what happens if the number of colors is just 1 more than the max degree? Then, can I get a bad example like this? No, it turns out. And then it always uniquely determines the space of coloring, so proper colorings uniquely determines the graph. That's what we're going to show. Okay? So that's the first thing. What we're going to show is that when the number of colors is at least the max degree plus 1, then the graph is identifiable from the space of colorings. And when k is at most d, then it's not identifiable. Well, actually, we just did that, right? I mean, I just showed you that side. I showed you the red side. I'm going to show you the green side. Okay?
It's a bit weird, right?
Oh, yeah. Why did I do it the other way? I put D there, and then I don't know, because that's my co-author did it that way, so I just copied. I was too lazy to change it, so. But that's why I put this up there. Is k at least d plus 1. This one is d growing this way. So you can look at one or the other. Don't look at both.
Does identifiable mean with high probability?
No, identifiable just means that if you get an infinite number of samples.
Okay.
Yeah, so it just means if I give you the whole space of colorings, does that uniquely determine the graph or not? Or is there, and if it's not identifiable, that means there's 2 graphs that have the same collection of, because I'm doing uniform distribution, I just look at the space of colorings. Okay? So, okay. So, I'm going to show you this, actually. Okay? But then, what else can we show? We can ask some further questions. First off, when I can identify it, how many samples do I need to do? Okay? So we're going to look at that. That's part 1 of the talk. And the other thing is, I mean, so for colorings, it's non-identifiable. I can look at other models, other problems, combinatorial problems, and I can ask for which ones is it identifiable for all graphs, okay? And we're going to get some characterization. So we can get some nice, simple characterization of which graph problems is it identifiable for all graphs or not, okay? So those are the two directions we're going to do in the talk. I just want to give you, before I'm going to talk about this, how many samples to learn. I want to give you some context about what's known for other things. So we have some context about how well we're doing or not. Okay? So this was studied especially for the easing model. So let me give you a reminder of the easing model if you haven't seen, or explain to you what the easing model is. Very simple. Comes up a lot though. So here's this graph again. I got two colors. Normally in easing model it's supposed to be +1 and -1, but it doesn't matter. We can call it blue and red, okay? And then just think of, I have this parameter B, and the weight of a configuration, a sigma is a coloring. So one of these colorings here. I got, I don't know how many, 10 colorings there or something like that, okay? Each row is a coloring, okay? Now, if you give me this coloring, so the point is that the monochromatic edge and a monochromatic edge. It's got two monochromatic edges, so that has weight B squared. Okay? This one has one monochromatic edge, so it's got weight B. This has no monochromatic edges, so it's B to the 0, weight 1. Okay? So that's the weight of these configurations. Now you look at the distribution proportional to these weights. Okay? That's the easing model, and that's the Gibbs distribution on this thing. Now the point is that if B is bigger than 1, then you prefer to have monochromatic edges. So that thing is called ferromagnetism, whatever. Anyways, and if B is less than 1, then you prefer to have the opposite color of your neighbor. Okay? So this one is easier. This one is easy. This one is hard. Okay? Oh, but the usual parameterization is instead of B, you have e to the beta, and then beta greater than 0 or beta less than 0. Okay? Is the usual thing. But it doesn't matter for us. So, okay, so now what's the learning problem here is I'm going to give you samples from this, for this graph. I don't know the graph though, but there is a graph which generated these, from which I generated these samples. Can you figure out that graph from these samples? Okay, and then, oh, well, yeah, here's an example where you might get screwed up actually. I mean, these 10 samples, the most likely graph for these 10 samples is this graph, because it's more often that these pair are monochromatic than this pair. So you might get confused. So it's not so easy. And then what's known for this thing? So it's known, so what is a beta is this, there was this B parameter which was e to the beta. Okay? And then, and D is the max degree of the graph that you're trying to learn. And then it's the running time of your algorithm is n squared log n times doubly exponential in d beta, d times beta. That was what Bressler did for the easing model. Okay. And then it was improved a little bit, well, in some sense. They got down from doubly exponential to singly exponential in d beta, but they got a bigger running time. And then there was this recent paper which shows that actually you can get singly exponential in d beta times n squared log n. And then there's a lower bound which is, well, it doesn't have the squared, but it shows that you need at least single exponential in d beta for the easing model. And they can generalize this to other models, Markov random fields, general Markov random fields. Okay?
This is the running time for what?
This is the running time for the algorithm to learn the graph. But if you ask how many samples it needs, it's n squared smaller. So if you drop n squared, then the number of samples they need to figure out the graph is, this is just drop the n squared. That's the number of samples you need.
High probability?
Oh, yeah. So you tell me there's an epsilon. Yeah, you tell me the epsilon, and you want to know it with probability 1 minus epsilon, and then there's some epsilon. I guess there's, well, certainly here there's an epsilon log n over epsilon, and then maybe is there? I don't know. Yeah, probably n squared over epsilon squared, something like that. Oh, actually, I think theirs is worse. I think the other ones are n squared over epsilon squared, and this one is maybe n squared over epsilon to the fourth, actually. So
n squared is because you
it's
every pair.
Every pair, yeah. So, but you can reuse the samples. So, but the number of samples, yeah. So yeah.
These two models are different, or?
No, oh, here. Well, no, actually, it's well, that was just easing model, and then this is more general. This is like any model, in some sense. Well, except colorings. It doesn't. Yeah. So I'll explain more actually what this means. General Markov random field in the next slide. But yeah, but this is more general. So and it gets it down optimally from doubly exponential to single exponential, and then there's a lower bound which roughly matches this. So it's got to be single exponential. Okay.
Why are you interested in easing model as opposed to, say, uniform random?
Oh, uniform distribution? Oh, well, then, yeah, but are you looking at the graph or the, yeah, what do you mean by uniform? Uniform over what?
All key colors.
Oh, k-coloring. So that's what I'm interested in. Yeah, so I'm just, yeah, but I just want to know, so I just wanted some context about how we're doing. So I think the thing I wanted to point out is this thing is, so it's exponential in d beta, and then in d. I mean, it's a key thing. It's exponential in the max degree. What we're going to aim for is, can we get it polynomial in d? And for these models, you can't get it polynomial in d. But for colorings, we're going to get it polynomial in d, actually. Yeah, so that's why.
Why are people interested
In easing model. Oh, yeah. Well, it's no. It's just a very simple model, and when you want to model something, it's just very natural because you got. I mean, the first thing that you're going to do when you model something is you're going to try just two possible states. That's what this does. It has two possible states, and then you're going to say whether they prefer to be the same or they prefer to be different. It's like they correlated, positively correlated or anti-correlated. And you can put a different beta on them, right? You can say this has some strength, this edge has some strength, and this one has a different strength. And you can have this one prefer to be correlated and this one prefer to be, negatively correlated, right? So you could do it like that. So it's a natural thing. But then you can generalize from there and you can say instead of having two colors, I could have Q colors, okay? So, but easing is what everybody starts with. Actually, and that's what they started with in statistical physics, was the easing model in the 40s. So, oh, and then you can look at other things like independent sets. Yeah, what's the big difference between independent sets and colorings from easing model? In the easing model, and in these Markov random fields, every color can be next to every other color with some probability. But in colorings, I can't be next to my same color. And in independent sets, if I think of it as color 0 and color 1, 0 for unoccupied and 1 for occupied, 1 cannot be next to 1. Okay, so it's a hard constraint. So these have hard constraints. They behave much differently than these soft constraint models. Okay? And then it turns out for independent sets, you can do something similar. You get d lambda, where lambda is the weight of the independent sets, and there's a lower bound which matches that. Okay?
So what you mean is, if you have a sampling of independent set with that way, you can run the graph. Is that right?
Yeah, that's right. Yeah. I mean, if the distribution, instead of doing uniform over all independent sets, suppose I look at the distribution where the weight of an independent set is lambda to the size of the set, and I look at it as a function of lambda, then I can learn that thing is called the hardcore model with parameter lambda, and then you can learn it in that amount of time. Okay, so what can we do for coloring? So yeah, so what we're going to show. Well, I guess I'll tell you later. Okay, I'll tell you in a minute. Yeah, what we can do for colorings is that we can do it in poly of dq. Instead of this exponential in d and q, we can get polynomial in d and q. Okay, number of samples in this whole region, k at least d plus 1. So that's the interesting thing. That we don't need exponential in d, but we only need polynomial in d for colorings. Okay? So.
What is Q?
Oh, yeah, why did Q is supposed to be k. Sorry. Yeah, sorry. Okay. Yeah, because I have another, yeah. actually, and we're going to look at this thing a little bit more general, which is, so I want to generalize these things. Because I want to say what models can we look at it for? Okay, so how am I going to capture? So I wanted some way of capturing this easing model and independent sets and colorings all together. Okay, so how do I do it? So I do something called homomorphisms. Okay, graph homomorphisms. Okay, well, which is coming up, right? You got some lectures, or you had some lectures, right? Yeah. Okay, so everybody's expert on it. Okay, so what?
But there's two improvements, right? Not just the time, but also you can identify with probability 1.
Oh, no, it's the same thing. It's with high probability. Because, I mean, you know, in the worst case, you might always get the bad. There might be like one bad coloring, and you might always get it with some probability. So I didn't state it formally, the result. I'll state it formally later, the result. So there is some dependence on the confidence parameter. You tell me...
Originally you said identifiability. If you know
identifiability says if you know all of it, all of this colorings, then it uniquely defines the graph. Now I'm saying that if you give me samples, how many samples do I need to learn it with high probability? And the number of samples I need is polynomial in D to learn it with high probability. Yeah. Okay. Oh, so what's the general setup? So easing model corresponds to this constraint graph. Let's say I have +1 is one color, -1 is the other color. Now, if +1 is next to +1, I have weight beta B. -1 next to -1, that has weight B, and then otherwise it's weight 1 between them. Okay, and you can think of a coloring or configuration as a mapping onto here. Okay, now what do I get for colorings? So in colorings, what's the model? Is I have, let's say I'm doing 3 colorings. Then 1 cannot be next to 1, but it can be next to the other guys. So I have, in general, if I have K colorings, I'm doing KQ, KK, okay, the complete graph. That's what it is. And I'm looking at mappings from onto there. And then if, in this terminology, what I'm doing is I'm looking at B as the adjacency matrix or the weighted adjacency matrix for this graph. So this one would correspond to 0s here and then 1s on the off diagonal. This easing would correspond to B's on the diagonal and 1s here. And then independent sets would be 1 cannot be next to 1, and then unoccupied can be next to unoccupied. And then if you want to throw in this weight lambda, then the way you do it is if it's D regular, you put a lambda to the 1 over D in there, if it's D regular. Because then every edge adjacent to it gets a lambda, and you multiply that D times, so you get a lambda factor. So you can generalize all these things by looking at this graph. The key thing is that these results I mentioned about, notice this easing model, the graph, what is it? It's the complete graph with all the self-loops, okay? And this one is on 2 spins. I can generalize it, and I can have Q spins. And I want the complete graph with self-loops, so we'll denote it like that. I don't know, is that the right way to do it? I don't know. I don't know, okay. Okay, you're the expert, I don't know. So all these results about Markov random fields, the graph is this. And then we're looking at graphs which are different than this. They have some edge missing there. There's some exclusion. There's some pair of colors which cannot be next to each other. Okay? It may be the color by itself, next to itself, like colorings, or it may be something else. Okay? So now, so I want to show you this thing. Okay? And then, then the other thing that we can show is that, then you can, over here, so the space of colorings does not uniquely define the graph. But you can say, who cares? I mean, why do I care? Maybe there's 2 graphs that have the same space of coloring, so why do I care which one you give me? Okay? Just give me one of them. Why do I care which one you give me? Okay? So what we show is that when you're below here, when the number of colors is smaller than this d minus square root d. Okay, the same threshold as before. Then the number, I don't care which graph you give me. I just want a graph which is equivalent to this, which has this distribution, this space of colorings. I don't care which one. I mean, there's many that are equivalent in this sense. I don't care. Give me a graph which is equivalent, but the time it takes to find a equivalent graph is exponential in n. So the number of samples you need is exponential in n over here, when k is smaller than d minus square root d. When k is bigger than, is at least d plus 1, then we can do it quickly. Okay? And then in between, we have some stuff, but we don't really know. Okay? So, but it's interesting that these two thresholds that come up from other contexts come up the same thing here. Okay? So, I want to explain to you this thing. I'm going to explain to you this one, and I'll explain to you this one, and then, yeah, we'll go from there. It's really easy proofs. So, okay? So I have a graph. I got k colorings. I got a bunch of random k colorings of this graph. I don't know the graph. I'm looking at a pair of vertices. I just pick a pair of vertices, u and v. Okay, and I just want to say, is there an edge there or not? How do I figure out if there's an edge? Well, if there is a coloring where they get the same color, then I know there's then I know there's not an edge. And otherwise, I'm going to say I think there's an edge. Okay, because that's all I can do. Now, I'm in the setting where, well, I haven't proved it, but I'm in the setting where there exists at least one coloring where they receive the same color. Okay, so there is some evidence that there's no edge between this pair. So take a pair where there is no edge. Then there is a coloring which proves it. But it may be that I need many samples to discover that. What am I discovering that there's an edge or not an edge? Discovering that there's not an edge. Okay. Yeah. Okay. Discover whether or not there's an edge. Yeah, right? Okay. So, okay. Oh, here was the example from before. I have u and v, okay? And before they always received different colors, even though there was no edge between them, okay? And now I want to increase the colors by 1. And I want to look at that example from before to get some intuition, okay? So what did I do? I put the complete graph on k minus 2 colors in the middle. And then there used to be one color left over, so they were the same. And then this is different from that. That's what it used to happen. Now I got two color choices. So the chance that they're the same color is 1/2. And then this guy has k minus 1 choices. So the chance he's going to choose the same color as over here is going to be more like 1/k. Okay? So it already changes so much once I just increase the colors by 1. Okay? That's going to drive our intuition. Okay? So what we're going to show is that when k is at least d plus 1, then for any pair which are not adjacent, the probability they receive the same color in a random coloring is at least 1/k times d cubed. Okay? Something like that. How do we do it? So take a pair, uv, which are not adjacent. Here's the graph. This is the neighborhood of u, neighborhood of v. They might overlap. Okay? It doesn't matter. What are we going to do? We're going to generate a random coloring here by rejection sampling. So what do? Take this new graph, rip out u and rip out v. And that's the new graph here. Okay? What I'm going to do is I'm going to generate a random coloring here, like a uniform from all proper colorings. Okay? And then I'm going to choose a random pair of colors for u and v. But those colors are uniform from all k squared pairs. They have nothing to do with the coloring here. Okay? Now if those are valid colorings with respect to this random coloring of g prime I just did, then that gives me a proper coloring of g, and I output it. Okay? But, I mean, maybe those colors I chose overlap with intersect with some of their neighbors, and then it's not proper coloring, so then just reject. Okay? The point is that the probability of generating any coloring here is the same. Okay? So if I generate, if I output a coloring, it's uniform, it's random, it's uniformly distributed over all colorings because every one has the same probability of being generated. Okay? So, okay, is that good? Because once you delete the color on U and V, then you got a unique coloring over here for G prime. Okay? So, okay, now what are we going to do? So we got to prove this claim. So basically, I have to just look at what's the chance that there is a color which is available, which does not appear in the neighborhood of U and does not appear in the neighborhood of V. If there's at least one color that's there, the chance I choose it for U and for V is 1 over k squared. So that's going to give me like a 1 over k squared factor. And then, so times the probability that a color does not appear here and does not appear here, which will be about d cubed. So that'll give me 1 over k squared d cubed. And then by symmetry over the colors, I'll get rid of one factor of k. So that'll give me 1 over k. So this is how we do it. It's just here, one slide. So, so the chance that they receive the same, that they can receive the same color, we want to prove that, right? Okay. So what are we going to do? Just a little bit of combinatorics, but it's elementary stuff. Okay. So I'm going to look at these. What do I want to look at? I'm defining this set A, C, I, J. That's the colorings of this graph G prime, where color C appears I times in the neighborhood of U and exactly J times in the neighborhood of V. Okay? I'm just defining that set. Okay? And similarly, I'm going to look at most I and the most J things. Okay? What am I trying to analyze? Look at A1, 0, 0. That means color 1 appears 0 times in neighborhood of U and 0 times in neighborhood of V. That means if U and V both chose color 1, it works in that case. Okay? So if I show that, then I get 1 over k squared times that. That's the probability we can color by color 1. Okay? So that's what we're trying to prove. So we're trying to prove that this thing is big. Okay? So how do we prove it? Well, okay, let's just do a little bit of basic calculation first. Okay? Get a handle on something. So I want to relate, like ACIJ, for any IJ, I want to relate to AC00. Okay? I want to say AC00 is not too small. Okay? So how do I say that? Well, I just do a mapping, right? I want to do a mapping from these guys to here. Okay? How do you do that? Take anybody that's color C, there's I here, and there's J here. Take those guys and just recolor them to something, right? Something else. How do I know there's something else? Because k is at least d plus 1, so everybody has at least one other free choice. So just color them to something else. That gives me a mapping from here to here. It's not, okay, it's getting recorded, so I'm going to use the wrong term probably. It's not injective, I guess, right? Yeah, right? I can't invert it, right? Is that the right one? Or ejective, surjective, whatever? Yeah, anyways. So it's not, I mean, I can't invert it, right? There's multiple things that map to the same thing, right? How many things map to the same thing? Well, I mean, try to invert it from here. How many things map to this coloring over here? Well, I have to decide I guys who got color C. So how do I choose it? Well, I gotta choose I from this neighborhood. There's D choices there, so it's D choose I. And then I gotta choose J from here, that's D choose J. So that's D to the I times D to the J. So, okay, so I get that inequality, okay? Okay, good. Doesn't look very useful. Anyways, but we're gonna use it in a second. Okay, now here's the more non-trivial one, but this is easy. Okay, look here. How many colors can appear at least twice here in this neighborhood of U? There's D vertices here. How many colors can appear most twice? At most D over 2 colors can appear most twice, right? And same thing over here. At most D over 2 can appear twice, right? Because I gotta fill up 2 slots for each of them. Okay? So there's at most D. Now look at the union. How many colors can appear at most twice here or here? At most D. Because there's most D over 2 here and at most D over 2 here. So there's the most D colors which can appear most twice. Therefore, at least K minus D appear at most once. So that means if I sum up these things, it's at least K minus D. Okay? That gives me that inequality. Now, I mean, this is for color 1, color 2, okay? and it's symmetric over the colors. So if I look at a specific color, then this likelihood is at least k minus d over k there. And then k is at least d plus 1, so that's at least 1 over d plus 1. So that's pretty good. It appears at most 1 time in each neighborhood. And I wanted it most 0 times. So now how do I relate that? Well, that seems pretty easy, because now I just use this basic inequality that I had here, right? Because, I mean, in order to appear at most 1 time, it either appears 1, 1, 1, 0, 0, 1, or 0, 0. And I just care about 0, 0, right? So, but how does 1, 1 compare to 0, 0? Well, 0, 0 is at least 1, 1 over d squared. So I'm going to pay at most a d squared. So to go from here, at most 1, 1 to 0, 0, I'm going to pay a d squared factor. And that's that. And then I'm done. So that's the whole thing. So we proved that it's identifiable, and we proved that there's an efficient algorithm. And the algorithm takes... Oh, okay, so here's the thing with the epsilon. So you give me an epsilon, and I want to know this, learn this graph with probably at least 1 minus epsilon. Then the number of samples I need is d cubed log. Oh, so it's just log of in epsilon. Okay? Yeah. So it must be the same thing for the Ising model too. Okay. So, okay? Okay, good. Okay. Okay. Oh, so let me give you some idea about this thing over here. So, I have this, I'm in this setting where these two graphs have the same set of colorings. I can't figure out which one it is, but I don't care. Just give me either one, okay? So, how are we going to show? Well, we're going to show an example. We're going to show when k is smaller than this, that the probability, there's a pair of vertices which are not adjacent, but the probability they receive is the same color, and therefore you know they're not adjacent. The proof that they're not adjacent, the probability of that is exponentially small in n. So that's easy to do when you give me arbitrary graph, unbounded degree. What do? I just take u and w. Just focus on u and w. I want to get u and w to have the same color, and then v is different from w, therefore it's different from u.
So, Eric,
Yeah.
maybe I missed something, but how did that probability bound?
Oh, the other
so
thing?
that you can get it in polynomial time?
Oh, this one?
Yeah.
Because I know what I've just proved is that in a random coloring of any graph, when k is at least d plus 1, that the probability that they get the same color in a random coloring is at least 1 over d cubed k squared.
Right.
So, oh yeah, so I just need 1 over the, yeah, right? Okay, so got it. Okay, okay. Oh, okay, so if we, back here. I want u and w to be the same color, right? Well, in this example, they're likely to be the same color. Why? Because if they got the same color, then everybody in the middle has k minus 1 choices each. And if they get different colors, then everybody in the middle has k minus 2 choices. So therefore, they're more likely to have, exponentially more likely in n to have the same color. And therefore, u and v are exponentially unlikely to have the same color. Okay? So that's an easy example. Okay, and what are we going to try to do? But the thing is, this has huge degree. So we got to simulate that huge degree somehow. So what are we going to do? We're going to put some big gadget here, graph here. Instead of w, put a big graph where order n of those vertices in the graph are guaranteed to be the same color. And then we'll do the same gadget for u. And then we got order n vertices guaranteed to be the same, order n guaranteed to be the same. And then in the middle, we'll just put these lines like that. But now there's an order n vertices, so we don't have to put like a complete graph kind of analog in there. We can just we can keep the degree bounded. Okay, so how do we do that? So, and this is the same thing that happens here. Actually, it's cool. So, okay, so it's kind of the similar example of before. I put the complete graph. I got k colors. Put the complete graph on k minus 1 colors. So there's 1 color left over. Put an independent set here of size square root k. Why square root k? You'll see in a second why square root k. Okay? It just optimizes something. Okay? So now what do you know about these guys? And now these guys, this independent set is connected to everybody in the complete graph. And what do you know? You know that this independent set, they all get the same color, right? Because there's only one choice for them. So they all have the same color. Okay? Right? Everybody got that one? Okay. Now what do I do? Now I make another copy, another complete graph with an independent set. Okay? But I want this independent set and this independent set to have the same color. So what do? I want to, these guys all have, let's say, color 1. So I want to exclude color 1 from all these guys. So I'm going to connect up these guys to here. Now I drew it just with one line. Okay? But actually, this guy should be connected to square root k over here. And this one is connected to square root k. So everybody over here is connected to one of these. Okay? And then if you figure out like what's the optimal size, the minimum size of this thing to maintain the minimum degree, then you want this size to be square root k. Okay? So, and now what we got now is that these are the same color as each other and the same as this independent set, and I can repeat this. Boom, 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 right? And then, okay, that's one graph. That's one gadget. Another gadget on the bottom. Now, these independent sets, same color, same on the top row, but there's no reason why they're correlated with each other. So I put these little lines just like before. And then they're going to prefer to have the same because then these guys get k minus 1 choices instead of k minus 2. And then it's the same thing. And then I just add on one guy, and then I don't know whether that green edge is there or not. So it's exactly, and there's many choices for that green one. So then what you get is that if you want to learn it with probability at least, even just with some exponentially small probability you want to learn it. It's not even with high probability. I just want to learn it with exponentially small probability. I need an exponential number of samples. So, okay. Okay. Whew. Any questions on that? Otherwise, I'm going to change gears, so you better ask now. 5 minutes on the last one. Okay? Anything? Okay, so I want to know, so colorings, it turns out that there's some graphs where you can't identify it for some range of parameters. Okay? I want to know for what sort of models can I identify it for all graphs. I got an infinite number of samples. Okay? So this is this color setting from before. I'm looking at these H colorings. This is the constraint graph for colorings. And then I can look at the constraint graph for independent sets. 0, 1 for occupied. So occupied cannot be next to occupied. This is independent sets. I'm going to do unweighted. So there's no lambda here. Okay, it's unweighted. And so I'm doing uniform overall valid configurations, uniform overall valid colorings, okay? And I'm asking whether it's identifiable for all graphs or not, okay? It's just, it's nicer to do unweighted graphs. You get a nicer characterization, okay? You can do weighted too, but it's just not as nice, okay? So what happens? Oh, so the first thing is, well, this one here, which I claimed there was an algorithm, right? Actually, it's not identifiable in general, right? Because, well, I mean, think about it. Actually, I mean, I brushed over this point before. Like, suppose B is 1. Then that means you don't care what your neighbor is. So then there's no way you can figure it out. So actually, all those bounds I told you, they assumed that B was bounded away from 1 and bounded away from infinity. And then the running time actually depended on how far away they were. And I ignored that. But now, so now if you talk about unweighted, if this thing is 1, then you can't tell whether there's an edge there or not. Okay? So we're going to exclude that thing. Because when it's the complete graph with self-loops on all the vertices, all Q vertices, Q is the number of colors, spins. Okay? Then it's not identifiable. Okay? So let's assume it's not. Okay? Okay, the first thing is, suppose there's some vertex has a self-loop. If some vertex has some color, not some vertex, some in the constraint graph, suppose there's a self-loop, like in independent sets, then it turns out it's identifiable. Okay? Let's do that. That's the easy proof. Okay? So what do? So suppose there is a self-loop, but not every color. So color I has a self-loop, but color J, let's suppose, doesn't have a self-loop. Suppose there's some color which does not have a self-loop. Okay? So then what do? I want to show that if there's, now you give me this graph, I want to show that if u and v are not adjacent, then there is a coloring of this thing. We call it H coloring because you're coloring it with this constraint graph H. Then there is an H coloring where u and v get an incompatible color. What does incompatible mean? That the pair of colors they get over here are not adjacent. Therefore, u and v are not, that's a proof that u and v are not adjacent. So in this example, I want a coloring where they both get color J. If they both get color J, then I know they're not adjacent because it's not consistent with H. Okay? So what do? I can just color this graph. What do? Because I color everybody in the graph red except for u and v. Because it's a self loop, so red can be next to be red everywhere, okay? And then, but then just u, and v. U and v, I'm going to color them with color J, okay? I mean color blue, which is color J. Now J cannot be next to each other. So if this is not an edge in the graph, then this is still valid. So it gives me a way to demonstrate, okay? So I can do that. Now also similarly, now suppose every color has a self loop. Well, I'm assuming it's not the complete graph, so there's got to be some edge missing somewhere. And I can do a similar thing. I mean, I find that structure and then I color everybody with this middle color. And then I color these guys, which I want to show that it doesn't have an edge, color with one of the colors and then the other one with the other color. And that the edge is not there. So it's a similar thing. That's the easy case. Now we're in the case where there's no self loop. Now what I do, okay? So now, okay, this is a little bit interesting, but it's still easy, okay? Okay, so what do? So I take this graph, I got this pair of colors, I and J, which are adjacent in this constraint graph, okay? So now I'm going to build a new graph. I want to know whether that edge in the constraint graph is really necessary or not, okay? So what do? I make a new graph. I'll call it Hij, okay? Because it depends on I and J. I'm going to do this for every pair. For every edge in H, I'm going to make a graph. Okay? Now, what does this graph do? I want to know whether this edge Ij is necessary or not. So what do? I make a copy of I, called I prime, and it's got the same neighbors. And I make a copy of J, which is called J prime. It's got the same neighbors for its structure, except I don't connect I prime and J prime together. Okay? And I want to know, is that edge necessary? So actually, if I take this graph, compared to this graph, which is the same, except I added in this one edge. Do they have the same space of H colorings on this graph? So this is my graph G, actually. My H is still the same, but I just constructed a G and a G prime. And I want to know on these graphs, do they have the same set of H colorings over there, okay? Okay? And now if they have the same set of H colorings, so in every coloring of this graph, I prime and J prime receive compatible. That means that the colors they receive correspond to an edge over here. Then that means whether I add in this edge or not, any coloring here is valid over here. That's what it means, that they're compatible coloring. If that's the case, then I can't distinguish this graph from this graph with respect to H colorings. So it's non-identifiable. So that's clearly non-identifiable. What we want to show actually is that this is a characterization. So I want to show the reverse. The reverse is actually true. So if it's non-identifiable, then actually there is a coloring. Oh, then in every coloring they receive compatible colors. So I want to prove that. Okay? So how do we prove that? So we're going to prove that by, okay, I'll just, I was here. I want to just do the contrapositive. So contrapositive says, it used to be that there was an IJ pair where all colorings of HIJ, they receive compatible colors. Now I'm going to say the negative of that is that for all IJ pair, there exists a coloring which proves whether or not this edge is there. Okay? Now, so assume that's true. Now what am I going to do? I want to take a graph G and I want to know whether UV is an edge or not. I want to show that I can identify this graph. So I want to show I can figure out whether this edge is there or not. Okay? So what do? So I need to show that there's an H coloring of this graph which proves that this edge is not there, that there's no edge there. Okay? Okay. So how am I going to prove that there's no edge there? I'm going to show there's a coloring where they get I prime and J prime. And then there's no edge between I prime and J prime. Okay? Okay, so what do I do? So remember, so what do we know? We know there is a coloring of this graph where I prime and J prime get incompatible colorings. So they cannot be adjacent to each other. Okay? So that's what we assumed. That was the hypothesis. So now what do? Take any coloring of G you want. It's an H coloring. Take any H coloring of G. It doesn't matter which one. And there's got to be at least one. Otherwise, it's not a very interesting question that we're asking. Okay? So there's at least one H coloring of G. And I want to show that there's an H coloring which identifies G. Okay? So take any coloring, H coloring of G. Call it S. Okay? Now, if the colors of U and V, I'm trying to find whether there's an edge. If those colors are compatible with each other, oh no, if they're already incompatible, then we're done. Okay? So if they get the same color, then we're done because we're assuming that there's no self loops here in this graph. Okay? We already took care of that case. So let's assume they're different colors. So suppose this one gets color I and this one gets color J. Now take that graph H for whatever I and J is, take that graph HIJ that you did, okay? There is an H coloring of this graph HIJ where I prime and J prime get different colors. So take that coloring and then replace U's color, instead of I, replace it with the color of I prime in that coloring. And V's color, instead of J, replace it with the color of J prime in that coloring. And everybody else, their color, if this was color 3, then I look at vertex 3 over here, and whatever its color is there, that's what I change it to. And then that U and V are not compatible with each other, so that proves that there's no edge between U and V. So it shows it's identifiable. So that's it. Okay. So that's the whole characterization. So there's a simple characterization for when it's identifiable or not. So, and then the last thing is, I mean, we had this in identifiable region, we had this efficient algorithm. Is that ubiquitous? Does that always hold for other problems? It turns out no. There are problems. We can make an example of a graph of a H coloring problem where it's identifiable, but to learn it requires exponential number of samples. So it's just something about colorings that we can do it. What is it about colorings? So our conjecture is that why did this hold? This was our conjecture going into it. Why? Because this would correspond to uniqueness. So that's our guess, is that when you're in a uniqueness region, then there is a poly of NDQ learning algorithm. So that's the key thing. And we have a little bit. There's something called Dubrusian uniqueness, which is a sufficient condition. It's not necessary, which implies uniqueness. And under that, we can prove that that holds, but it's, still far from the whole thing. So, okay.
Thank you.
Okay.